All right, welcome back, everyone. Welcome back to Calculus 2. So last time, we introduced the concept of sequences, and I show you two different type of sequence. One is arithmetic sequence, and another one was a geometric sequence. So if you guys remember the difference between arithmetic and geometric sequence, the pattern, right? For the arithmetic sequence, you keep adding, or keep subtracting the same number to find out the next the number. But while geometric sequence, you are keep multiplying or keep dividing same number to find out the next number. So that was a difference between arithmetic and sequence. So we pretty much understood what the sequence means. And then you need to find out the generalized form of each sequence. So today, what we're going to do in 5.1, we are going to check whether the given sequence is a divergent or convergent, okay? So if you remember, so we're going to talk about the sequence. Oopsie, I'm going to get rid of it. So let's say we have a sequence, and then you have a general form, which is AN. It could be, arithmetic sequence or geometric sequence. So the common number is going to be the plus minus some number for the arithmetic sequence, but geometric, you're multiplying or divided. So that your job is to find out the general form. And then what we are going to do, if you keep writing, right? So the general form going to give you some number, A1, A2, A3, whatever. I want to know whether, right, this list of the number are keep going increasing or decreasing. I want to know whether they have a certain number that they're heading to. So the concept is I'm going to take the limit in front of the general form. And then because you are keep writing and you're keep finding the next number. So as n approach to the infinite number, where this number is actually heading to. So you have a two option. One is convergent. Another option is a divergent. So what that means is you found out when you take the limit of AN, and then you found out they're heading to a certain number, then you said it is a divergent sequence. If you don't have some number that they're heading to, it's going to be divergent sequence. So we are going to talk about how to determine the given general form of the sequence is convergent or divergent sequence. So that's our goal today. Does it make sense? So first step is you're going to have a given sequence, okay? And you're going to check it out, whether it is a convergent sequence. Simply, you're going to take the limit. And then if you can evaluate the limit, and then the limit L exists, if it exists, it is going to be convergent. If there's no limit, automatically it's going to be the divergent sequence, okay? So let me show you the example, more concrete example of this topic. So I'm going to give you the sequence AN, and then they say AN is 1. So what does it mean? AN1 implies that N is 1, A1 is going to be 1. No matter what N, AN is going to be always 1. Although N is equal to 2, it's going to be 1. N equal to 3, A3 is going to be 1. So that's what the general form saying that. So therefore, let's say this is N. As N increases, your outcome is fixed. It's always 1, right? And then I want to know, is there limit of AN? So let's rewrite it. According to the definition of the convergent, we have limit and approach to infinity, an, and we just found out that an is 1. Am I correct? So what is a limit 1? This is a constant. If you remember in calculus 1, the outcome of the constant is a constant. It's going to be 1. Doesn't matter. No matter what the n, your outcome is always 1. This function is heading toward the 1. So this is the limit. We have exactly the number for limit. So what type of the sequence? This is exactly convergent sequence. So that's how you decide whether it is a convergent or divergent sequence. I'm just showing you one popular example. Okay, so the way to see whether it is a convergent divergence, take the limit. As n approach to infinity, do I have the limit of that? Yes, then it is a convergent. No, then it is a divergent. Does it make sense to you? So I'm gonna keep solving more practices regarding to this topic. I'm gonna give you a little bit of time. If you got this concept, can you show me your thumbs up? Does it make sense to you? Yeah, sounds good. So let me show you another example. So as I mentioned, we already discovered that theory. Give a sequence an to define whether it is a convergent. You're gonna take the limit with the generalized form. This idea came from the limit concept, okay? So once you have the general form, take the limit as an approach to infinity and look at whether they have a limit or not. So another example, I'm gonna look at that. Okay, we have a function, and thank you, they already found out the an, the generalized form, is a 1 over n, right? So what does it mean? If n is a 1, so I'm gonna write it an equal to 1 over n means n equal to 1, 1 over n is 1. So a1 is 1. If n is a 2, a2 is gonna be 1 over 2. If n is a 3, a3 is a 1 over 3. So what does it mean? As n increases, 1, 2, 3, 4, 5, we start from 1 and half of it and 1 over 3. They're getting smaller, 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 smaller. And you're gonna look at the limit of this function, correct? Therefore, we have a given an, so limit as n approach to infinity an mean we have 1 over n, correct? And now you can consider, right? You can consider this one as a function. As n increases, what happened? The outcome is getting smaller, 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 smaller. They are getting close to the 0, correct? So 1 over n, if you remember, in calculus 1, as x approach to the infinity x, it is always a 0. Do you remember that? So therefore, it is going to be 0. And you can see in the graph, as n increases, they're getting smaller, 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 getting close to 0. So therefore, 0 is a still number. This is a still number. So the limit is equal to 0. That's your limit. Therefore, this an is a convergent sequence. So 0 does not mean that divergent. They're heading toward the 0. That means getting close to 0. Still, your limit existed. Okay? So it is a convergent sequence. That's all. Okay? So likewise, we're going to keep practicing a couple more examples, whether it is a convergent or a divergent. So let's take a look at 2 more examples. So I'm going to hold up here. Does it make sense to you? If you got that one, I love to see your invisible thumbs up. All right, let's do 2 more. Okay, I do have sequence. Thank you. They already found out the generalized form. So let me write down a couple list of the numbers of that. So when an equal to -1 to the n over n. So if n is 1, a1 will be -1 to the 1 over 1. will be -1. If n is a 2, a2, -1 to the second over 2, +1 over 2. Am I correct? Just keep on going, a couple more example. Negative to the odd number, it's going to be -1 over 3. So you see the pattern, what is going on? If n is a 4, a4, -1 to the 4 over 4, +1 over 4. So what is going on? This is the pattern. A1 is -1, A2 is 1 over 2. So if you look at this graph, just draw as n increases. When n is 1, the A1 was a -1 right there. If n is a 2, they're going to be positive but getting smaller. And then n is a 3, they're going back to negative, smaller. And then they're getting close. If you keep on going, they're close to the x-axis. So up, down, up, down, up, down, up, down, up. But the gap is getting narrow down, isn't it? So it looks like they're getting approached to a certain number, which is a 0. But I'm going to rewrite it. Limit n approach to the infinity, an. So we have an. -1 to the n over n. So we found out in the graph, as I mentioned, minus, positive, but they're getting smaller, close to the gap, which is a 0. Getting close to 0, this is the limit. Limit existed. Okay, so we observe that the outcomes close to 0. We observe that the outcomes close to 0. So therefore, this is also convergent sequence. That's our period. Okay, so making a graph will be really helpful, right? This one was a constant, so it is a 1. They're getting smaller, close to 0. Also, they're up and down, but getting close to 0. Okay, so let's do another example. I'm going to give you guys time. All right, so far so good. Same pattern, the generalized form is already given. Thank you. So an is -1 to the n. So when n equal to 1, a1 is a -1 to the 1, which is a -1. N equal to 2, -1 to the second, +1. N equal to 3, -1 to the 3, -1. Just one more, n equal to 4, a4, -1 to the 4, +1. So exact pattern, -1, +1, -1, +1 as n increases. So we have 1, -1, +1, -1, +1, -1, +1. I don't see any narrow gap or increasing gap. They're creating the same constant line 1 when n is even number. Everything is going to be -1 when n was odd number. Do you see that they are getting close to any certain number? We have a 2 number. One is a 1, another one is a -1. So what does it mean? They have 2 different direction. We don't have any certain L. So L, limit n approach to an, and then we have 2 different directions. We found out -1 to the n. What happened? We have a 2 different direction, plus minus 1. This is not going to be the limit. 2 different direction means limit does not exist. Okay, so that means many people confuse, hey, Professor Ben, they're anyway going to 1 and -1. No, limit must be one answer. You have to head into only one number. This is a 2 different direction. This is not no limit. So therefore, it is going to be divergent. This is a divergent example. This is sequence. An is a divergent because you have 2 different directions. There is no limit. Okay, so that's the example I really wanted to add in 5.1. So I'm gonna hold up here. If you guys are happy with that, I love to see your thumbs up. I'm pretty sure you guys okay with that example. So we good. We practiced couple examples, and then now, since the limit concept has been reoccurred in calculus 2, we can also think about the limit law with the concept of the sequence. So the following is here. So just so you recall, we talked about long time ago in calculus 1. Let's say you have a limit with the an general. Let's say you have a general form of the sequence an, another general form of the sequence, let's say bn. Let's say both of them are convergent. So the generalized form an sequence is there's a limit. The generalized form of the b sequence also has a limit. If then the following properties are all true, okay? So this is the constant, c equal to constants according to the limit law. Doesn't matter, it's a 1, 2. So example, limit and approach to infinity 100, the outcome is 100, right? Or 1,000, it's gonna be 1,000. So constant is always the constant as an outcome. Okay, C is a constant, you can bring them up to the front so that this is going to be already has a limit A, so it's gonna be CA. You can also add and subtract inside and outside of the parentheses. So this means you can separate by using the distributive property. So this one has a limit A, this one has a limit B, so A plus B. Also, you can multiplication. This is A, capital B, so you can multiply or add and subtract. Also, you can divide it as well. So this is a simple limit law. If each the general form an, bn has a limit. So this is very simple concept. We learned already in calculus 1. I'm going to apply this one in the following example. Okay, so we're going to literally take the limit to solve the example. So let's go to the example. Okay, here we go. Determine whether the sequence converges or diverges. Okay, so this means you need to take limit as the n approach to infinity, take it out, whether it is a convergent or divergent, right? So we're gonna take a look at it. Oh, I'm not deleting. So if it is, there is, if there's a limit, if there's no limit. So that's what it is. So let's look at the first one, letter A. We have an, so we're gonna take a limit. So limit n approach to infinity. So an is a 5 minus 3n to the second power. I want to know whether it is a divergent or convergent. So I can separate it according to the limit law. So it is going to be limit 5 minus limit 3 over n second power. Are you okay with that? And I can bring 3 to the front. So again, limit with the constant, what did I say? It's going to be 5. And then 3 to the front, limit 1 over n to the second power. And just hold up here. Do you guys remember this one? Note, if you remember long time ago, in calculus 1, if you have a limit and approach to infinity 1 over x, this is the function, right? 1 over x or 1 over n doesn't matter. You can change this one n. This is a 1 over n graph. As x approach to the positive, what happened? They're getting close to 0. So this is going to be 0. How about limit? If I do have a limit and approach to infinity 1 over n squared. So the graph, it's a positive, up. So as n larger and larger, still they're getting smaller. It's also 0. So this is you learning calculus 1. This is a fact. 1 over n with the limit as n approach to infinity, or 1 over n second power. they're heading toward the 0. So therefore, this is going to be 0 as well. So I can rewrite it. I'm gonna rewrite this. This one, 5 minus 3 times 0. This is a 0. The answer is a 5. So this is going to be, so the AN is a convergent sequence. We prove it. Okay, they are close to 0. Convergent sequence to 5. That's the letter A, how you check with the complicated AN. Okay, sounds good. So I'm gonna hold up here. Can you show me your thumbs up? Does it make sense to you? That's the letter A. Gotcha. All right, so let's go to letter B. Oh wow, this is AN. They already create a generalized form for us, which is good. We don't need to find out, it's already given. So to find out whether it is a convergent or a divergent, we need to take a limit, right? So let's take a limit. N approach infinity, 3n to the 4, 7n to the second, plus 5 over 6 minus 4n to the 4. How would you be able to take a limit? Do you guys remember that? So one strategy, you can take a limit with this complicated fraction. If you remember calculus 1, divide by the highest degree to everywhere. Okay, so in this time, let me look at it. We have n to the 4, n to the second, n to the 4. So what I'm saying, the highest degree is n to the 4, correct? You're gonna divide it by n to the 4 with every component. So watch me what happened. You're gonna do equal. Oh, actually I need to write limit. 3n to the 4 divided by n to the 4. 7n to the 4 divided by n to the 4. Actually, that was a n to the second. Plus 5 over n to the 4. Over 6 over n to the 4 minus 4 n to the 4 over n to the 4. Are you following? That's what I'm saying. You're going to divide it by the highest degree n to the 4 with every term. That's how you are going to simplify the limit. So what happened? Rewrite it. So limit and approach to infinity. We have simple 3 minus 7n to the second over n to the 4. And 5, there's nothing you can cancel. 6 over n to the 4 minus 4 because n4 and 4 cancel. Now we're gonna take a look at the step here. What does it mean? We have n to the second divided by n to the 4, 5 divided by n to the 4, 6 over n to the 4. If you have a highest degree in the bottom, same thing, 1 over n to the second, no matter what. I'm gonna just make a space here for your better understanding. So if you remember, I'm gonna copy this. Okay. You have all this knowledge. Limit and approach to infinity 1 over n. Limit and approach to infinity 1 over n second. Limit and approach to infinity 1 over n to the third. Whatever, keep going. Everything is a 0. Right? We just proved that from the calculus 1. So therefore, if you have having higher degree in the denominator in limit goes to 0 all the time. For example, limit and approach to the infinity, I do have n over n to the third. The denominator degree is higher. Doesn't matter, it's going to 0. Same thing, limit, if I have n over 6, n over 3, the denominator degree is higher, it's always a 0. This is the low property, if you remember in calculus 1, right? Or you can think about the property, numerator or denominator with the limit. We have 3 scenario. If a numerator is less than denominator, we just said that. For example, x to the 2 over x to the 5th, the limit is always a 0. How about the numerator degree is higher, such that x to the 5th over x to the 2nd, limit undefined, does not exist. What if we have equal, like x to the 5th over x to the 5th? You're gonna read the coefficient of each fraction denominator, okay? So this is the strategy, how to take the limit with the complicated fraction. So therefore, keep in mind this information. So therefore, what happened here? The denominator, everything is higher. So this is gonna be anyway 0. This is gonna be 0, that is a 0. So the conclusion is, we have a limit and approach infinity. Just we have a 3 over -4. This is a constant, so the answer is going to be -3 over 4. So this is also an is a convergent to -3 over 4. That's your conclusion. Very important question. So I'm going to hold up here so that you can digest. Actually, I'm going to minimize it for you. Oh. So we are not going to be confused. Yeah. Okay. So I'm going to hold up here so that you can digest this information. Letter A and B. You are taking the limit of the general form of the sequence. We are tracking whether it is a convergent or divergent. If you have existed L, that's a convergent. If they are not heading toward any number, it's going to be divergent, usually 2 directions or multiple directions. So especially taking the limit, many people forgot. So I told you, if the denominator is higher, always the limit is a 0, right? So check it out, like a 1 over n, 1 over n to the 2nd, 1 over n to the 3rd, they're all going to 0. Because having a higher degree in the denominator in limit goes to 0. But if the opposite, limit does not exist, if it is equal, for example, limit, if I have 2x to the 2nd, 4x to the 2nd, same degree, top and bottom, you're going to just read the coefficient, 2 over 4, they're going to be 1 over 2, still have a limit. So limit is going to be the coefficients. So that's what you learn in calculus 1. If you took my calculus 1, we spent a long time how to evaluate the limit like this. So anyway, this concept still apply in calculus 2 with the sequence topic. So I'm going to hold up here letter A and B. So if you got that one, I love to see your thumbs up. Very important question. So I'm going to spend 3 more examples like that. I'm not going to give you too much information because we need to understand what we are doing clearly. So if you got that one, I love to see your thumbs up. Does it make sense to you? So if you join a little bit late, definitely watching this video will be really helpful. So check it out. The main idea, what we are doing here, we are still in 5.1. We're tracking whether the given AN is a divergent or convergent sequence. And a little bit of, limit concept from calculus 1. So are you guys happy? Does it make sense to you? So no worry, I'm gonna show you more practice. So we're gonna do more example together. So let's do the following example. I'm gonna go down slowly. So I'm gonna make a short video today because this is important topic. So let's take a look at 3 more. So yeah, it's the same question. So let me go up. let me copy this. So this is the same type of question. We are checking whether the given generalized form is a convergent or divergent when you take the limit. If there's an L, it's going to be convergent. If there's no limit, it's going to be divergent. So let's do this work. Letter A. AN is a given. Thank you. So we are going to take the limit because I want to know whether it is a convergent, divergent as n is getting larger and larger. So we have a 2n over n to the second. So here, it's very interesting because when you look at the numerator, as n increases, 2 to the 1 is the first number, 2 to the second, 2 to the third. So they're getting larger and larger increase. So it looks like they're getting infinity, infinity, infinity. Okay. How about the denominator? N 1 to the second, 2 to the second is a second number, 3 to the second. This is also increasing. They're getting also infinity, infinity. So what does it mean? It looks like when n is getting larger and larger, the outcome looks like infinity over infinity. Oh, this one is what? If you remember, this is indeterminate form. This one, you need to take indeterminate form means we need to use L'Hopital's rule. What does it mean? This is from calculus 1. So if you have indeterminate forms such as infinity over infinity, infinity over 0, whatever undefined form, these are all undefined form in terms of the limit. How would you be able to make the conclusion infinity over infinity? What is that meaning? This is undefined. If you have that kind of case, we have to use L'Hopital's rule, which means you are going to take the derivative, both numerator and denominator. So then you are going to simplify. Do you remember that? Very important. So I'm going to take the derivative for each top and bottom. So here we go. I'm going to rewrite here. Let me minimize it a little bit. So here we found out limit n approach to infinity, 2n over n to the second is an indeterminate form. So you need to take the derivative n to the n over d over dn n to the second. I'm taking the derivative, both the numerator and denominator. Does it make sense? So what happened? If you remember the note d over dx, b to dx, what happened? You keep the b to dx, ln b. So this is the rule. So therefore, the top here, it is going to be limit n approach to infinity. You have a 2 to the n, ln b. Over, what is n to the second? You will get just 2n. Okay. So now, let's take a look at it. As n increases, right? As n increases, they keep going larger and larger. So I found out the second. So this one, when you look at the numerator, 2 to the 1, 2 to the second, they're also getting larger and larger. The bottom is also getting larger and larger. I have, again, indeterminate form. You have to take L'Hopital's rule one more time. Okay, so let's take a look at the L'Hopital's rule. So actually, I need a little bit of space. So I'm gonna keep going here. So you're gonna take the L'Hopital rule. So I'm gonna keep the same color. Limit n approach to infinity, d over dn, 2 to the n ln b. And then you are taking the derivative top and bottom, 2n. So let's take a look at it, the numerator. What happened? This one, you're gonna use the product rule, isn't it? So this one, oopsie. Here, we have to use a product rule because we have two functions multiplied to each other, 2 to the n ln n. So f equal to 2 to the n. F prime will be 2 to the n ln b ln 2. Let's say g equal to ln b. G prime will be 1 over, what is it? We have ln. So I think I need to change this number. Sorry about that. So this is ln b. B is already given 2. So this is a 2. So let me change this one too. So just change everything, ln. This is ln 2. So therefore, it is going to be 1 over 2 g prime. Are you following here? So let me highlight it. So this is the product rule. F is a 2 to the n, so f prime is a 2n times ln 2. G is ln 2, g prime should be 1 over 2. So according to the product rule, what happened? I'm gonna minimize it a little bit. So what happened here? You have f prime. So we have f prime g, g prime f. F prime 2 to the n ln 2 times, or I'm gonna write it in the bottom here. This is f prime times g ln 2 plus g prime 1 over 2 f. We have a 2 to the n. So that is going to be f prime plus g prime. So if I rewrite it, 2 to the n ln 2 to the second plus 1 over 2, 2 to the n. And then just so you know, that's your numerator, right? And then what happened, the denominator, this part, this is going to be just a 2. So therefore, I'm going to write everything here. So therefore, this one, so this is the numerator. So the entire outcome we got, and 2n is going to be 2. You have a 2 to the n, ln 2 to the second, plus 1 over 2, 2 to the n. Are you okay with that? I'm going to make a space. So now we are taking the limit of it. So let me just go back to the question. This is a double L'Hopital's rule, so you might be confused. So what I'm saying is, when I look at the AN, it was an indeterminate form, infinity over infinity as n increases. So therefore, I took the L'Hopital's rule, which means that you need to take the derivative with numerator and denominator. So that's what I did, and I got this part. And then as I increase n again, this is still infinity over infinity. So I took the second L'Hopital's rule. So I'm taking derivative top and bottom. So we got this outcome, limit n of infinity. So this is a numerator and denominator. Are we okay? So now we found out the limit. The denominator is a 2, correct? 2n become 2. And then 2n ln 2 second 1 over 2, 2 to the n. Now as n increases, the numerator is not going to be increased, just 2, right? Same number. And then this one is getting larger and larger, larger and larger. So we have infinity over 2. So what does it mean, infinity over 2? Infinity divided by whatever the number is infinity. So thus, we prove that limit n approach to infinity 2n over 2, 2n over n to the second, which is our given an, is going to be larger and larger. This is going to be divergent sequence to positive infinity. That's the conclusion. So we just proved that this sequence is a divergent to infinity. So couple work as you need to consider, right? This is a 2, and this is the numerator. So we got the divergent at the end. So I'm going to hold up here. You need a time to understand. Does it make sense to you? So think about it. Think about it. All right. So that should be okay. If you got this question, can you show me your thumbs up? Does it make sense to you? How you feel? Everybody okay? So please, this is the combining calculus 1 and 2. We are checking whether the given sequence is a divergent or convergent. So you need to check, right? Here we have to use L'Hopital's rule because it was an indeterminate form, infinity over infinity. We don't know what that is. It's hard to define. So therefore, using the L'Hopital's rule, you keeps making simplify, 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 then you can define where they're actually heading to. There's no limit. It's infinity. So it is a divergent. Okay. All right, two more. Letter D. Okay, so let me go to here. I'm going to actually use different color. So B, we have an e to the 2n over n. So we want to know if it is a convergent or divergent, right? So let's take a limit and approach to infinity, e to the 2n over n. Am I right? So let's look at the numerator, denominator separately. As n increases, they're getting larger and larger. E to the 2, e to the 4, they're getting larger and larger as n approach to the larger number. So this is going to be infinity. How about the denominator? N, 1, 2, 3, 4, 5, as n increases, getting increases too. Dun, 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 dun. This is infinity over infinity. Again, indeterminate form. So we're going to use L'Hopital's rule again. So you're going to take the derivative of each one. So what does it mean? Limit and approach to infinity, d over dn, e to the 2n over d over dn, n. So we are taking the derivative top and bottom separately because it is going to be the L'Hopital's rule, right? So what happened? So a little bit of note. D over dx e to the x, if you remember, it's e to the x. D over dx e to the nx, you have n times e to the nx. So this is the note. So therefore you can apply what happened when you take the derivative of the numerator, you have a bring 2 and then keep 2 e to the n over n is going to be 1, right? So simply it is a limit and approach to the infinity, 2 times e to the 2n. I'm going to bring 2 to the front. So we have e to the 2n. So what does it mean? E to the 2n. As n increases, this is going to be larger and larger. So 2 times infinity is infinity, correct? Doesn't matter whatever you multiply, number with the infinity is infinity. Therefore, an is a convergent. Oh, sorry, not convergent. It's a divergent, my bad. An sequence. So the an sequence is a divergent sequence to positive infinity. That's your conclusion. So that was the second example B. Does it make sense to you? That was it. That was letter B. Okay, are you so far so good? Does it make sense to you? So I'm going to do slowly and surely that should be clear. All right. If you got this one, I love to see your thumbs up. I hope everybody's doing right. All right, one more example. There's one more example. I'm going to change the color to green. The C. So let me write it here. We do have an cosine n pi over 2, right? So let's check whether it is a convergent or divergent. So we're gonna take the limit. So n pi over 2, right? Oh, actually, I'm missing cosine. My bad. So there's a cosine, right? That's the function. That's your given an. And check it out. This is a cosine function. So if x or n equal to 1, this is a cosine pi over 2. N equal to 2, this is a cosine 2 pi over 2 is going to be pi. N equal to 3, this is a cosine 3 pi over 2. N equal to 4, cosine 2 pi. N equal to 5, cosine 5 pi over 2. So that's something we can check. And then what is a cosine pi over 2? Go to decimal or look at the pattern. So the cosine function has 1, and then this is -1. Every 2 pi, you will see the same pattern, right? So if you go to the decimal, cosine pi over 2 is actually 0, which is here. Cosine pi is actually -1. Cosine 3 pi over 2, you're going to come back to 0. Cosine 2 pi, you will come back to 1. So what I'm saying is 0, -1, 0, 1, 0, -1, 0, 1. They're repeating. So cosine 5 pi over 2, just check with the decimal. It comes back to 0. Right? So what is it? This is sequence 0, -1, 0, 1. 0, -1, 0, 1. They're keep going the same thing. So what do you guys are seeing? They have many multiple different direction. So this one, we have a multiple different direction. So when you take the limit with those pattern, they're not fixing one number. They're not heading to a certain number. They're heading toward this pattern with the multiple directions. So therefore, AN is divergent sequence. That's the conclusion. Usually trigonometric function of your AN should be divergent sequence because they are going up and down, up and down. So this pattern, if you go going up and down, up and down, up and down, they keep going up and down. There's no limit. They have a multiple different direction. Okay, that's it. That's how you practice how to evaluate the limit in terms of the sequence. Okay, so this question should be all right. So if you got that one, I love to see your thumbs up. Does it make sense to you? Yeah. So now I'm going to do one last example. I'm going to finish at 5.1. I don't think we're going to move on 5.2 because the 5.1, you need to make a time to really review that. So let's talk about the last theorem, squeeze theorem in terms of 5.1. So maybe you heard about the squeeze theorem or sandwich theorem in calculus 1. So what, if you remember the simple idea, this is a very simple idea. You have an order with the following function. AN is the smallest function, BN is in the middle, CN is the largest one. You are going to take the limit to each function. If AN is heading to C and CN is heading to also C, where the BN function is heading to also C, because the first and last function are going toward the same limit. Therefore, the middle sandwich need to go to the same limit. So we call this is a squeeze theorem. And this theorem is still applying into the limit concept, limit of the sequence concept. So I'm going to look at that. We have an order, AN, BN, CN order. And then if AN, the first and last function has a limit, automatically the middle BN has the limit at the same limit as well. So this is a very popular theorem, as you've been seeing so many times. So let's look at the example. I have a question. We have AN. This is the sequence. There is a list of number. And then thank you. They already found out the general form of the AN, cosine n over n to the second. they want to find out where they're actually heading, whether it is a convergent or divergent. So this one, right, cosine n over n to the n. Well, you can think about numerator and denominator separating. If you found out the indeterminate form, you're going to take the L'Hopital's rule. There got to be a way to do it, as we just look at the previous question. But in this question, I'm going to use squeeze theorem. Okay, so let's set it up. So we are trying to know where an, so let me change the color. I want to know where the limit an, which is a limit cosine n over n to the second. I want to know whether this is the divergent or convergent, correct? It's a little bit complicated function, cosine n over n to the second. So one way, we're going to use this fact. According to the cosine function, this is the cosine function. Cosine has a maximum always 1, minimum is always -1. If you remember from the trigonometry, so cosine, and this is a fact, is going to be between -1 and +1. Am I correct? And then we have a specific order. -1 is the smallest function, cosine is the middle, 1 is the largest one. And then what I'm going to do, I'm going to divide it by n to the second in each term. So let's see what happened. It is going to be -1 over n to the second, cosine n over n to the second, 1 over n to the second. I'm trying to find out the same format. Now you're going to take the limit. You're going to take the limit of each. So I'm going to just minimize it a little bit. So what happened? If you take the limit n approach to infinity, where the -1 over nx second heading to? Actually, I'm going to write here. And then I want to know the middle one, actually, right? We want to know cosine n over 2n. This is n second. This is what I want to know. And then we have a specific order, limit 1n to the second. So what happened here? What happened here? If the first, last are equal to, the middle is automatically going to be the same. So we know this, guys. I spent so many times this one where they're going to 0, right? As n increases, that fraction going to be 0. Therefore, the middle sandwich also 0. So you don't need to do any other work. Just use squeeze theorem, help us to find out the answer directly. So therefore, this sequence, an sequence, converges to 0. This is a convergent sequence. So we just use a squeeze theorem, sandwich theorem. Does it make sense to you? So that's how you can prove it. One more example here. So I have limit, I want to know an is a given, thank you, -1 over 2 to the n. I want to know whether it is a convergent or divergent. So I'm going to use the squeeze theorem. So what happened is you have to find out other two functions with the same order. So first of all, you can think about this way. What if I have -1 over 2 to the n is going to be in the between middle. And then you have another order. So I'm going to create it. What if I have here 1 over 2 to the n negative outside? So this outcome is always smaller than this one. This is a positive outcome. This is a negative outcome. Another one is I'm going to just have a positive 1 over 2 to the n. So this is a specific order. You can use 1 over 2. And then I'm going to keep the limit -1 over 2 outside n. Now we're going to take the limit -1 over 2 to the n. Limit 1 over 2 to the n. So what happened? We just know where they're going to. So this means limit -1 to the n over 2 to the n. And then we're going to keep this one, copy, paste. And then it means limit 1 to the n over 2 to the n, right? So this is getting close. If you just go to decimal, if n is 1, it's going to be negative some 1. If it is a positive, it's 1 over 4. So they're keep negative. It's getting to be like this, smaller. And then this one also, 1 over 2. They're getting smaller. Just check that information as n increases because of the negative, whatever the outcome is going to be negative. So they're going to be something like that, getting smaller, close to 0. And then this is outcome is a positive, but they're still getting smaller to 0. That is going to be 0. This one is going to be 0. Therefore, the answer that we are looking for is also 0. So thus, AN sequence converges to 0. That's our finalized answer. Okay, that's all. So we finished with 5.1 fully. So it's an introduction of the sequence. I really want you guys take a look at all the questions that I show you in the last video and today's video. So now you have a better confidence doing all the quizzes. So they're also embedded video. You can watch that. So please make sure that, you can finish 5.1, and next week, we're gonna move on 5.2